Howdy, everyone. Hope that you guys' Wednesday has started out well. I want to go ahead and say thank you all very much for coming to class. Today, what we're going to do is we are going to finish chapter number 5. And with chapter number 5, we've gone over a lot of stuff. And it might seem like, oh man, like this is just one chapter. It is. We spent a lot of time on lots of different things. And I want you to kind of appreciate that as okay, that's how I should think about preparing for the exam. So don't think about, oh, well, I'm going to weigh chapters 3, 4, and 5 equally. Instead, say, you know what? We spent 2 days on chapter 3, we spent 2 days on chapter 4, and then we spent like 5 days on chapter 5. I think I'm going to spend a lot more time on chapter 5. And the reason for that is all of the things that we covered in chapter 5 are super critical for chemists. One of the most important things that we talked about in chapter number 5 was we talked about moles and we defined a mole. We looked at the periodic table, and I'm going to grab from another window something from the periodic table. Um, and, I recommend this right here. Okay, so here we've got boron. If we look at this on the periodic table, thanks for nothing, PowerPoint. I don't need that right now. If you look at this on the periodic table, I want you to be able to take away a couple of things. I want you to, whenever you see a symbol on the periodic table or, one of these little squares, these cells on the periodic table, I want you to say, I know exactly what that means. For example, the 5, we know that that is the number of protons that an atom of boron has. This 10.81 is a little bit tricky. This is a couple of things, and they're all kind of true at the same time, though they might seem a little bit different. 10.81 is the average atomic mass of mass, not moss. Um, it's the average atomic mass of an atom of boron. Okay. Now, if I showed you this 10.81, there's also a possibility I might round it up to 11, in which case you'd say, okay, well, that's the atomic weight, and that is equal to the number of protons plus number of neutrons. And when you see that, and when you see the two things that I presented on the screen so far, and the two things being this and this, you might say, okay, well, 10.81 as an average number, that makes sense because, I've taken three numbers and if you like baseball, I've calculated a batting average. I've calculated an earned run average. And I'm saying if you like baseball because I like baseball and tonight is opening night of baseball season. Um, you might look at those numbers and say, oh, okay, well, yeah, I can understand 10.81 is an average value. Got it. But then, wait a minute. You just kind of randomly decided to round it up to 11? And then you gave us this definition that I'm familiar with, but how are those two things simultaneously true? Well, the reason is because of isotopes. If you remember, isotopes are atoms of the exact same element with different masses. So there's an isotope B12, B11, B10. All of these are boron atoms, but could anyone tell me in the chat what makes these things different from one another aside from the number? What does that number represent that makes them different from one another? The 10, 11, and 12. Why is there 10, 11, and 12? And I can give you a little bit of a Vivian, spot on. Great job. So the number of neutrons. And Cameron, absolutely. Great job. So it's the number of neutrons. And this average atomic mass is taking all of these different isotopes and saying, okay, well, in the known universe, 25%, and I'm just randomly coming up with numbers here, 25% of all boron isotopes have a mass of 10, 35% are 12, and that would leave me with about 40% that are 11. So that's how this number is calculated. And I know that you guys have done that, but it's been a little while. We've had a spring break, we've had a test, we've had a lot of time since then. Okay, so that's one important part. And another thing that makes this number significant is this is the mass of 1 mole of boron atoms. Now, when we talk about the mass of 1 mole, we're going to say this is 10.81 grams. Whereas over here, when we're talking about mass and average mass, the units that we would use would be 10.81 AMU. The number does not change, but the unit does. So if you were to see a multiple choice question that is, um, here, let me, the mass of 1 mole of boron atoms is A, 10.81 AMU, B, 5 AMU, C, 5 grams, or D, 10.81 grams. I would want you to, right from the jump, just go ahead and say, well, 5 is wrong. Because I'm talking about mass, and this number reflects the number of protons. That 5 is the number of protons. The question, now I got to go back to it. Okay, got to think about this one. The mass of, ooh, oh, well, oh, dang, I can't really, those numbers are identical. One of them's right, one of them's wrong. The mass of 1 mole, aha. 1 mole of them means 6.02 times 10 to the 23rd atoms. And this says, okay, 1 mole of boron atoms, aha. The correct answer would be D. Okay, so this I think is, that's one of the heavy lifts that we've had this chapter, and it's a big conceptual thing to clear. Um, so I want you to be kind of thoughtful of like, I'm going to give myself time on this just to kind of process it gradually and slowly. Now, with that in mind, we are going to pivot, though not crazily. We are going to be moving on to talk about solutions because more times than not, um, when you are thinking about like a liquid or something, it's actually a solution. Now, when it comes to solutions, and we're going to come back to moles, this is going to be related to moles in just a little bit. Um, but what we've got is a solute versus a solvent. So this is a terminology difference. The solute is salt, for example, and the solvent is water. So I always like to think about this as the thing that gets dissolved. That is the solute. The solute gets dissolved. Now, the solvent, I always, for some reason, what's stuck in my mind is the thing that solves. And of course, of course, we're not talking about actually solving anything, but instead it dissolves. So the thing that dissolves the other thing is the solvent. A solution, like salt water, is a mixture of that. It's got a solvent and a solute. Now, if you just got pure water and compared that to tap water, and I'm going to write tap water, as opposed to H2O. Because whenever I'm saying pure H2O, that means there's nothing in there. When I think of solvent, I think of chemicals like paint or paint remover. Nice. Yeah, that's a great way to think about it. Because if you think about or sorry, I'm, yeah, that's a great way to think about it. Um, you know, the paint remover would effectively be the solvent, and then whenever you kind of collect the paint in a container with the paint remover, that would be your solution. So I like that. Thank you very much for sharing that, Grayson. So when we've got pure H2O compared to tap water is going to be a solution because that is going to be, it's going to have lots of stuff dissolved in it. You know, if you ever hear a conversation about hard water versus soft water, in Central Texas, we navigate and deal with that a lot because we've got lots of limestone. We've got lots of dissolved minerals in our water. In some communities, there's fluorine in your water system. In I mean, there's lots of other just kind of random minerals, not random, but they all relate to kind of where's that water coming from. You know, our water sources are coming from, or most of Central Texas's water sources are like from aquifers, and so you're going to have lots of dissolved minerals in there. Whereas if, let's say that you got ocean water, you can't drink ocean water. It's too much salt in there. But there are some places in the world where they reclaim ocean water and then they put it through a desalination plant or a desalination process. So they take a solution like ocean water and they basically remove all of the salt and anything else that's in there to get pure water. And then they're going to have to add things back in there, or they more than likely will add things back in there. Um, One thing that I always think about whenever I'm comparing like pure water or pure H2O and tap water is I always think about um, distilled water. You can buy distilled water at the grocery store. Um, and distilled water is something that is really good for, if you have a humidifier. I have a little kid, so we have a humidifier that goes next to his crib just so that, he doesn't get too congested. A humidifier, and then see some people have a continuous pressure device, a CPAP machine. And distilled water is going to be great for those because what's happening is that these devices, these instruments, the humidifier and CPAP machine, what they're doing is they're kind of making water vapor from that water that you supply it with. And if you use tap water for that, well, then you're going to have lots of salts accumulate. Salts accumulate. And those are going to, be problematic for that instrument or for that machine. Okay, so your takeaway from this is I want you to know an example of a solution. Something right off the cuff where you can say what that solution is and then immediately kind of come up with, okay, well, here's an example of a solute in that solution. I like Diet Dr. Pepper. Just between the 86 of us, I actually like regular Dr. Pepper, but I think that it's better for me typically to drink Diet Dr. Pepper. Really, it's better for me to drink water, but nevertheless, whenever I think of a soda or something like that, I think, okay, well, um, what's my solvent? Water. Water is still the solvent. Okay, what's my solute? Ooh, well, with a soda, it's not just there's not just a single solute. Instead, with a soda, you're going to have things like caffeine might be a solute. Another solute might be like I don't know, like a coloring chemical or a coloring agent. Um, and so those two solutes are going to give that the appearance and the flavor. And so another solute might be a flavoring compound. And these two are the ones coloring compound and a flavoring compound or chemical, where then people start hearing chemicals and they're like, chemicals are bad. Salt is a chemical. Um, at any rate, let's move on. So when we talk about solutes and solvents, we want to get into and be familiar with the term soluble versus insoluble. Now, if something is considered to be soluble, we're going to put it in some context. Like here, soluble in water. So we're defining a solute and then in the solvent. And what I mean by that, and one thing that I want you to kind of think about with respect to that is there are many things that are soluble in water. Sodium chloride, also known as NaCl. That's an ionic compound that will go into solution very well. Ethanol is also something that is soluble in water. Sucrose, a sugar, is soluble in water. Now, something that is insoluble in water would be something like propane. Okay. Now, what I want you to take away from this right here is these two formulas, these two compounds. This one on the left is ethanol. Ethanol looks like this, CH3. So this is the CHHH. Here's the next CHH. So CH3, CH2, and then this red ball represents an oxygen, and then this white represents a hydrogen. So CH3CH2OH is ethanol. Now, sucrose, I don't need you to worry about sucrose because that's something like C12H22O12. But again, don't worry about that. Now, what I want you to recognize in comparison or as a comparison of ethanol to propane is propane has one, two, three carbons. One, two, three, four, five, six, seven, eight. So that's three carbons. So I'm going to write this formula as C3H, what did I say, 8? Huh. What's the difference between ethanol and propane? Well, one difference is number of carbons. Okay. But if you, well, actually, no, we could go ahead and add to that number of carbons and number of hydrogens. But we could also look at this and say propane, ethanol is in gasoline. Ethanol is an example of an alcohol, and it might be a part of, yeah, absolutely. So if you go to, Grayson, I'm happy that you brought that up. If you go to Buc-ee's and you're getting gas, because let's all face it, when you go to Buc-ee's, there's about a 30% chance that you're actually there for gas. There's about a 70% chance that you're there for like 5 pounds of brisket, 10 pounds of candy, and a soda. And if that's not you, that's fine. Um, so we've got, let's say that you go to Buc-ee's, there's going to be the row of gas pumps, GASPUMPS, and some of them will say no ethanol. And then others will say something like up to, I think it might be up to 10% ethanol. And that's just so the ethanol is an alcohol, and your car can burn a small amount of it and get some energy from it because ethanol, what ethanol also is the alcohol in beer, wine, and kind of liquor in general. Um, and what do we know about the alcohol, or what do we know about, let's say, liquor? If you put it next to an open flame, or actually, heck, you got a lighter and you dipped that lighter into, I don't know, something like tequila or something like that. There's enough alcohol in there that it's going to burn. And so essentially what that means is that this will burn in your car's engine. What is it going to do? Well, it burns alcohols. It burns alcohols to, get the engine moving. Um, it's not just ethanol. There's other components. I'm happy that Grayson, thank you so much for bringing that up because gasoline is a solution. Gasoline is a solution of gasoline is a solution of alcohol, alcohols, and hydrocarbons. And just as an example, when you go to the gas station, and let's say you go to the pump and, you know, there's unleaded, there's premium gas, and then there's super unleaded. I drew these little boxes because what do you usually see next to the pump? See a number. Unleaded might be something like 87. Premium might be 89, and then super unleaded might be like 93. Could you give me a one in the chat if, hey, I've seen those before? Okay, so those numbers are what's known as an octane rating. And I'm not an organic chemist, nor am I a gasoline person. I mean, I have a car that uses gasoline. But basically, these numbers are a little bit of a measure of levels of contaminants, and not contaminants that are going to be super harmful to the average car engine, um, but basically how much octane is in there. Octane is an example of a hydrocarbon. The higher the number, the higher percentage of that mixture or that solution is octane. And I bring that up and I want to bring that back because we identify things as being soluble in water or insoluble in water, as is the case with propane. But let me tell you this, octane is a liquid at room temperature. Room temp. And octane is just a bunch of carbons. I'm going to put CX, HY, a number of carbons, a number of hydrogens. And propane is soluble in octane. Okay. So whenever I say that, I mean that C3H8 and CXHY, I'll give you the actual formula for octane, C8, and that is H18, if I remember correctly. Yes. So that is octane. Propane will dissolve in octane. Propane will not dissolve in water. And that's because of, or that's explained with this principle right here. Like dissolves like. And you could say, oh, well, this is just a bunch of carbons and hydrogens, so they're going to dissolve in there. But another way of putting that is a polar substance dissolves in a polar solvent. So a nonpolar a solute, like propane, nonpolar, will dissolve in a nonpolar solute or solvent like octane. So what I want you to take away from this slide is this concept and this idea right here. Like dissolves like. If something is classified as polar, it's going to want to be in a polar solvent. Another thing is if something is ionic, like NaCl, ionic substances dissolve in polar solvents. So before we go on to the next slide, you might look at that and say, well, where does sucrose and ethanol, where do those fit in? Well, sucrose and ethanol, by having these oxygens right here and right here, they are somewhat polar. So they're going to like to dissolve in something like water. Now you might say, oh, but well, you were just talking a moment ago about how ethanol is going to be found in gasoline. It will be. Ethanol is kind of a tricky compound because, yeah, it's got this OH, didn't mean to do that, but it's also got these hydrocarbons. So ethanol is somewhat polar and somewhat non-polar. So it can kind of do both things. All right. Now we're going to go on to, so I want you to understand like dissolves like, and I want you to be able to think about whenever I'm defining something, I want to find a similar solvent for it. Okay. Now, these solutions right here, give me a 2 in the chat if you agree with the statement that these solutions are different. Perfect. Now, I think that if I told you that these were Kool-Aids, I think most people would say, well, this one right here is probably going to be the sweetest, and this one right here is probably going to be the least sweet or least flavorful. Um, and I think that if someone brought you this right here and they said, hey, it brought you some Kool-Aid, and you're like, okay, cool. Well, I don't really like it too sweet. I think that most of y'all are familiar with, well, what you would do. If you really wanted the Kool-Aid, but you didn't want it so sweet, you'd probably say, okay, well, I'm going to add some water to it. And you would add water, and this could be tap water, no problem there. And you could either get it to this or get it to this. And I think that most folks would understand that what they are doing in that process is they're using, well, they're diluting the solution. They're diluting this right here to look and taste more like this right here. So they would dilute it by adding water. Now, if you're not familiar with the term dilute, well, I want you to be, and that's what that means. Effectively, you're adding water to make something less concentrated. So we can describe these solutions. We could use either the term concentrated or we can use dilute. Now, this is showing the more concentrated solution on the far left, and I'm going to write on the far right here the less concentrated solution. Now, the less concentrated solution is also referred to as the more dilute solution. Now, the more concentrated solution is going to be the less dilute solution. So just think about these as kind of inverse of one another. Now, when it comes to chemistry, we quantify making a solution. Now, here's an example. If you were to follow this, this is linked. This simulation gives you the opportunity to make a solution. And I'm going to go ahead and do that real quick. I'm going to share what that looks like. So here what we have is our drink mix. Yes, we're going to add drink mix. Oh boy, as you can see, it's getting more and more dark red. We can look at the solution concentration and we get a number. We're going to talk about that number in just a minute. If I wanted to make this solution more concentrated, so if you think about it as Kool-Aid, more flavorful, I could either add more drink mix, or what I could do is if you look in the lower, kind of the lower left-hand corner of the screen, I could get some of that solution to evaporate. Because when this solution evaporates, all that's really leaving is the water, the solvent. The solute, the drink mix is not going to evaporate. So I'm going to adjust this. Notice that concentration goes up. At some point, that solution will become saturated, which is what you're seeing at the bottom here, little crystals of that drink mix. And whenever I make this water evaporate more and more, what's happening to the concentration? At some point, it stops changing. Now, if I have a very concentrated solution and I add water, well, I can continue adding water, and at some point, or sorry, that concentration is going to go down. Add more drink mix, it becomes more concentrated. Now, with that in mind, could anyone tell me, or actually, let's see, we've got approximately, let's see, this right here would be half a liter. This would be 1 liter, so 0.6, 0.7, 0.8. So we've got about 0.8 liters of this solution. So that's the total volume that we've got. If we were to remove some of the solution, one thing before you think about the outcome of this, um, if I were to remove some of this solution, I want to look at this and say, okay, well, um, actually, let's just imagine that you were able to shrink yourself down to like a microscopic level and look at the solution right here, and then look at the solution right here, and look at the solution right here. Give me a Y or an N. Are these different areas? Is the solution going to be effectively identical? Yeah, we know that it is. And that's another way of saying that this solution is homogeneous. So no matter where you are in that solution, it's absolutely identical. Now, what that means is that if I remove some of this solution, so if I remove the liquid, I'm removing the solution. I'm not selectively removing the solvent. So if I were either to like scoop a cup in there, or if you see down here at the bottom, I've got this valve, I'm going to open that valve up. The volume will change, but the concentration will not. Let's watch that. Boom. I went down to 0.6 liters. My concentration did not change. I can go down to zero point 0.5 liters, zero point 0.4. The concentration is not changing. Okay. So whenever it comes back to this right here, this question, how can we change the concentration of this solution? There's a couple of different ways. We could add more drink mix. Okay. The concentration could also change by evaporating the solvent. Okay. Evaporating the solvent would cause the concentration to go up. Adding more drink mix would cause the concentration to go up. The last way that we could change the concentration is add more solvent. When we add more solvent, that causes the concentration to go down. So I'm going to say over here, add more drink mix, the concentration goes up. Evaporating solvent, concentration goes up. Add more solvent, concentration goes down. Okay, now with that, we have this number, this concentration, And whenever I was doing that simulation, you probably saw that you saw a number something like 2.874 moles per liter. So this right here is known as molarity. And that is moles of solute per liters of solution. Now, molarity are our standard units for concentration. Now, you've probably seen other examples of concentration units. Maybe you've seen something like milligrams per milliliter. That's a concentration unit. But that's not what a chemist uses, I'm sorry. And you might think, well, why? Can a chemist use this? Yeah, they can, but they have to convert it back to this. And why is that? Well, because chemists arguably only care about moles. And then they care about moles related to a total volume of the solution, which would be liters. Moles are the important units that chemists are interested and care about. So whenever you're doing a calculation, and we'll do some in just a moment, we'll do a couple of them, you always want to relate it back to number of moles per liter of solution. But you might see this number written as, like I said up at the top, 2.874 moles per liter. This is the same as 2.874 with a capital M indicating molar, which this is also the same as 2.874 moles 1 liter. So I want you to be kind of comfortable toggling between those and recognizing what those are. Now, what we're going to do is we'll just go down here to do a calculation. What is the molarity of a solution made by dissolving 2 moles of NaCl in enough water to produce 0.5 liters of solution? Okay. So I know the first time that I read this sort of prompt, I say, okay, what's the molarity? All right. Where I want you to go with that is I want you to immediately think moles per liter. That's my answer. My answer is going to be in moles per liter. The next thing is by dissolving 2 moles of NaCl. Oh, okay. Well, that's kind of cool because it's giving me the number of moles. So 2 moles. I don't know how many liters though. Then it goes on to say 2 moles of NaCl in enough water to produce 0.5 liters of solution. Huh. Okay, so I'm going to write my definition for molarity. Molarity is equal to moles solute divided by liters of solution. Now, in order to answer this question, we have to find what is our solute. Well, that is 2 moles of NaCl. Our solute is NaCl. How many moles of that? 2 moles NaCl. Then it says we're dissolving it in enough water. Enough water? That's not an amount. But okay, to produce 0.5 liters of solution. That right there is maybe the most important part of this question. And that brings us back to the language of our equation. This tells us liters of solution. Well, what that means is that this 2 moles of NaCl, that's a solid. As soon as you add water to it, it's going to dissolve. Now, does a solid take up space? Yeah, absolutely. So when something takes up space, is this like 1 milliliter of space? Is it 2 milliliters of space? We don't know. And we don't need to know really. Because what we're doing is we're saying, this is the way that you make a solution. This is going to be a very strange shaped beaker. The total volume here is 0.5 liters. I'm going to give you, actually, I'm going to erase this and give you two different options. And I'm going to ask you the question, how to prep a solution. And I want you to think about times that you've made a solution. We've got two different options. One option is that we're going to say, okay, 0.5 liters of solution. I'm going to get my graduated cylinder here. I can get another graduated cylinder over here. How are we going to prep a solution? Step one, add water to 0.5 liters. Okay, so let's go ahead and say that's right here. So I'm going to add water all the way up to 0.5 liters. And then step two, add, well, this tells us 2 moles NaCl. And step three, move forward in life. Okay, so that's one option. And you might think, okay, cool, that sounds good. Another option is, I'm going to call this step one, add 2 moles NaCl. And I'm going to put, here's my marker for the 0.5 liters. Step two, add water to 0.5 liters. And then step three, move forward with life. Okay, so I'm going to call these option A and option B. Which do you think is the correct way to prep a solution? And if you're unsure, put C. But if you think it's A, put A. If you think it's B, put B. If you're unsure and you're just sitting on the edge of your seat to find out, press C. Okay, so I'm getting a good mixture. Most recently, I'm seeing lots of A's. Now, I'm going to tell you right now, the correct way is B. And I want you to think about, let's kind of change the the parameters just a little bit. Um, what we want is 0.5 liters of solution. That is the same as 500 milliliters. 500 milliliters is not 501. It's not 499. It's not 495. It's not 505. We want exactly 500 milliliters of solution. Now, if we were to go through the process in kind of part A, for step one, add water to 500 milliliters. What volume of water would that take? That would take, requires 500 milliliters of water. Now here's where I'm going to change the parameters just a little bit. Let's say that our beaker or our glassware that we had, if you went above, or it holds exactly or precisely 500 milliliters. So if we did step A and we filled it up, it's like filled to the brim. The kind of, like if you move the glassware at all, some of it's going to spill out. So we do step one, and then we go on to step two, and we add this NaCl. As soon as we add that NaCl, what's going to happen to the solution, to some of the solution? It's going to overflow. Exactly. So then in that case, well, yeah, we'll overflow. We'll end up with 500 milliliters of solution. But let's imagine that rather than this piece of glassware, just a second. Sorry. Um, if we did it with this piece of glass where we add the 500 milliliters, but then we added the NaCl, that's going to cause the solution to come up here. So then we're looking at like 505 milliliters of solution. So if we are looking to make exactly zero point 0.5 or 500 milliliters of solution, what we want to do is we want to add the solid down here. And that then add H2O up to this line. Are we adding exactly 500 milliliters of water? No. But let's look back at the problem. How much water are we adding? We're adding enough water. This question never asked us about how much water are we adding or how much water is needed. This is just saying, hey, you need to add enough of your solvent, water, to get to 500 milliliters of solution. Okay. Can you give me a 1 if that makes sense or a 2 if that doesn't make sense? Okay. Now, we're going to skip down to slide 11. Slide 11 shows us the specific sort of glassware that we would use. And we're going to go through the process of making a solution. This substance is copper sulfate. And we're asked, what is the concentration of this solution? Now, in order to answer that, I'm going to grab the symbols from the periodic table. So let's calculate our molar mass of this, because what we want to do first is we want to figure out the number of moles that we've got. This tells us that we've got a total of 1.2 grams. The molar mass, capital MM, of CuSO4 is going to be 63.5, I'm going to call it 0.55, plus 32.1, plus we've got times 1, times 1, times 4. I'm going to round that up to 16. 16 times 4 is 64. So this is 4 times 16. So 63.55 plus 32.1 plus 64. And so what we're looking at there is 95.65 plus 64. And that would be 100.65, 959.65. That is my molar mass of copper sulfate. So if I had 1 mole of copper sulfate, that would be the mass of it, grams. Now, what I want to do is I want to figure out how many moles of copper sulfate I have. So I'm going to do the dimensional analysis, 1.2 grams of CuSO4. This blue solid right here is what copper sulfate looks like. So copper sulfate, most copper containing compounds, as opposed to like pure copper is like, it's got that reddish, hate to say it, but that reddish copperish color to it. Copper-containing compounds typically are kind of blue. We've got 1.2 grams of CuSO4, 159.65 grams of CuSO4 is the mass of 1 mole. And on my numerator, 1 mole CuSO4. So I'll take 1.2 and divide it by, or 1.2 times 1 is 1.2. Then I'm going to divide by everything in the numerator. So 1.2 divided by 159.65. What did I get? 0.0075 moles of CuSO4. Okay, now I'm going to write this up here, 0.0075 moles of CuSO4. So that's less than 1 mole. I don't need to worry about how many atoms or molecules that is, but that's what I've got. Now, this shows kind of the flow that you would do to properly prepare a solution. This piece of glassware that I'm circling is a piece of glassware that's a specialized piece of glassware. This is known as a volumetric flask. Now, what's difficult to see here, and I'm going to erase this, but I'm going to zoom in on this one of them. What I want you to see, and this is kind of tricky to see, but I hope that you can see it. I'm trying to point to I'm pointing to a etched line on this piece on the neck of this piece of glassware. Can you give me a 3 if you can see that, or an S if no, I can't see it? Okay, great. Now, that etched line right there denotes something. This piece of glassware has a marking on it that says 100 milliliters. 100 milliliters is the same as 0.1 liters. If you added a solution up to here, up to this etched line, that would be exactly 100.00 milliliters. Now, if you're anything like me, and the first time I saw this piece of glassware, I'll be completely candid with you. The first time I saw a volumetric flask, I said, that's the dumbest piece of glassware I've ever seen in my life. I haven't seen a lot, but so far, that's the dumbest. And the response that I got was, well, why? And I said, this is a piece of glassware that if you end up exactly on that line, that's exactly 100 milliliters. Great. Okay. But what if you have a drop above that? Well, then you could say it's more than 100. What if there's a drop below that? Then it's less than 100. How much more or how much less? Well, you don't know. So that's why I kind of had a negative opinion of this piece of glassware, because essentially this specific glassware, and they make different volumes of them, but they are good for one thing and one thing only, making a specific volume. That's it. So a volumetric flask is only as good as what's on there. Can everyone give me a 9 if, okay, I understand that. And I'm not going to disagree that it might cause some problems. So this is a piece of glassware that's very good for making a precise measurement. So it's very precise. That doesn't mean it's not dumb, but that just means that it's very precise. It will get 100 milliliters, and that's it. If you go above, well, is it 101 milliliters? You don't know. If you're below, is it 99? Is it 95? You don't know. You just know that it's above or it's below. But With that in mind, despite my own personal opinion on this piece of glassware, it is a very good piece of glassware for accurately preparing a solution. The way that you do this is you get your solid, you measure out the mass of your solid, and you add it to a volumetric flask. What I want you to notice is that when you add this solid to that, there is no liquid in there. So it is completely dry. So you're going to add the solid first. So step one, and this is basically how to properly prepare a solution or precisely and accurately prepare a solution. You add your solid. Step two, whatever your solvent is, which chances are it's going to be water, you're going to add 50%. And I'm going to say, put a tilde there to mean roughly 50% of total volume, solution volume. Okay. So that's where we are right here. This is step one. This is step two. Step three, what you want to do is you want to swirl it. You want to swirl the solution to get solid into solution. Step four, well, that's just kind of a, okay, now we're ready. So I'm going to put this as step 4 and 5. Step 4 is add solvent to exactly 100 milliliters. Or I'm just going to say to exact or to desired volume. Okay, so step 1, add your solid. Step 2, add roughly half of the solution volume. Step 3, swirl. Step 4 is going to be add your volume to the total desired volume. So going back here to which is our sequence, we always want to add the solid and then add water to it because that's going to give us the desired volume. And when we go back to this calculation, molarity of our solvent, or sorry, molarity, what we're doing is we're looking at the solid that is in the total volume of that solution. We're not asking about, well, how much solvent did we add? And when you look at and when you prepare a solution, the volume of the solvent that you add, you might not know. It doesn't matter because that should just be water, or chances are it's just water. It doesn't matter that you added 498 milliliters of, or sorry, it doesn't matter that maybe you added 98 milliliters of water because the solution's volume, the combination of the solvent and the solute is 100 milliliters. Could everyone give me a 7 in the chat if, okay, now it makes a little more sense, or okay, I've got it, and give me a B if that still doesn't make sense. And if you're like, well, this still doesn't make sense, then what I want you to do is I want you to go to your kitchen, get a cup, fill it at to the absolute highest with water, and then get a cup of sugar. Add that cup of sugar to that cup with water that's filled to the top and see what happens. Then report back. And then do the opposite. Get the cup of sugar, add it to the cup, and then bring the cup up, the volume of the cup up to the top. Don't do any of that because that's a waste. And it will just make a mess, a very sticky, unpleasant mess. Okay, so now to complete this question, what's the molarity? What is the concentration of the solution? We've got our number of moles, and then we've got our volume. So we would say our molarity is our moles of solute, 0.0075, moles CuSO4 divided by, what's our volume? Our volume is 100 milliliters. We need this to be in liters of solution. So we're going to say 0.1 liters. So 0.1 liters. So we divide 0.0075 by 0.1, and we get 0.075 molar. That is the correct answer to this question. Okay. Now we'll do two more molarity calculations. Then we're going to do another calculation. We'll move on. And that will be it for the day. What is the molarity of a solution made by dissolving 10 grams of NaCl, so into 1 liter of solution? So I'm going to get Na, or that right here. And I'm going to give you this information. I can give you a second to work on it, and then I'm going to work on it as well. And then we'll reconvene. If you're not done, don't worry about it. And if you want to work on it uninterrupted, then mute me. Okay. What is the molarity of a solution? So what is the big M made by dissolving 10 grams? Okay, so dissolving 10 grams, so that's our solute. So 10 grams NaCl. But I'm going to need to convert this to moles in 1 liter of solution. Okay, in 1L. So the volume I don't need to mess with. So that's going to be 1L. Now 10G NaCl. What is the molar mass? I'm going to say that's 22 point, I'm going to call it 23. I'm going to call this 35.5. So that would be 58.5 grams of NaCl is 1 mole NaCl. And clear that out. 10 divided by, or 10 times 1 divided by 58.5, and I get 0.17 moles NaCl. Okay, so there's my moles of my solute divided by 1L, and I'm done. So 0.17 molar. That is the molarity of my solution. All right. I'm going to move on to the next question. What is the mass of NaCl required to prepare 0.5 liters of 2 molar NaCl solution? Okay, so here what we have is a tricky question. This one's kind of like, we're starting here, we're going there, but then we're going to end up back here. You couldn't see any of my hand motions, but that's what it is. So our volume, we need to make 0.5 liters. Our molarity calculation is going to be moles solute divided by liters of solution. We're not asked about, or our question is asking about 0.5 liters, though. Wait a minute, that's a little tricky. So what is the mass? Oh, and then mass of NaCl. Okay, so here's what we need to do with this question. We need to figure out how much of our solute we will need if we're only making half a liter. This value, the big M, will be the moles of solute for 1 liter, not for 0.5 liters. So essentially, what we can do is we can take this right here, 2 molar NaCl, is equal to 2 moles NaCl in 1 liter. We can multiply this right here by this. The reason we can do that is we can say, all right, well, 0.5 liters is what we're given. We can treat this as a dimensional analysis problem and say our molarity, this definition, this is our conversion factor. We need 2 moles NaCl per 1 liter. So 0.5 times 2 is going to be 1. And that's our answer. Because these liters, they'll cancel out. And that's kind of our objective with dimensional analysis. So essentially, this question is asking, what is the mass of 1 mole NaCl? And that one, all that we have to do to do that is say, well, again, I'm going to round this to 23, and this is 35.5. So that would be 1 mole of NaCl is 58.5 grams. Could everyone give me a 9 in the chat if they followed that? And a Z in the chat if I'm a little mixed up on that one. Okay, so we've got 2 more types of calculations. Percent concentrations, which actually I'm going to save that for the beginning of class on Monday. We'll do dilutions. So a dilution calculation is just this right here. M1V1 equals M2V2. And this is basically a way of saying, hey, you are going to take one stock solution. So this M1, this is our stock. And you're going to make a new solution. So this would be like, I don't know if you've ever, let's just imagine, I always like to think about Kool-Aid. Not like always, but for this example, I like to think about Kool-Aid. Let's say that you got, 6, let's say that you got enough Kool-Aid to make a 10x solution. And you might be thinking, well, what do you mean 10x? I mean 10 times as strong as regular Kool-Aid. So if your basic Kool-Aid is one packet of Kool-Aid makes 1 gallon of Kool-Aid of drink. Does everyone understand this right here? There's my definition. And I'm going to come back to this 10x solution. Give me a 3 in the chat if you understand my definition here. Okay, now I'm going to come back to my 10x solution. This 10x solution or this 10x Kool-Aid, I've got 10 packets and I've added them all to 1 gallon of drink to make 1 gallon of drink. So this is super strong. Give me a 1 in the chat if you follow that and a W if you think, ooh, I would like to drink that. I'm seeing 1s, no W's. I understand that. Okay, so this is a super strong Kool-Aid. This would be a 10x solution. If somebody came up to you and they were like, okay, cool, you've got this super strong Kool-Aid, that's great, but I just want a 1x. I just want a regular Kool-Aid. Could you make that from this? Could you prepare that? Give me a Y or an N. Yeah, you could. And what you would do is you'd say, okay, well, I'm going to take one, and I'm not going to use units. I'm going to say 1 part of super strong Kool-Aid. And then what am I going to do to that one part? Am I going to do anything or just say, go ahead, drink it? And this is a little bit of a longer response, but add to the chat what you would do to that one part. Add water. So it'd be, would everyone agree with me that since it's a 10x solution, be like one part of strong Kool-Aid and 9 parts water? Give me a Y or an N if you understand that and you would agree with that statement. That would get us our regular Kool-Aid. Great. Now, what happens if you were to add 12 parts water? Well, it'd be too dilute. They wouldn't like it. Maybe they wouldn't revolt or anything, but they'd be like, "Oh, this wasn't the 1x Kool-Aid that I wanted." That is the same thing as this calculation right here. That principle is this. Now, the difference is that we take molar concentration and different units and we quantify it. So we have our stock solution. This would be our 10x Kool-Aid. Now, the volume of this we don't really care about, but this stock solution, well, it's in this 100 mil volumetric flask, and what we're going to do is we're going to take 10 milliliters out of it. So we're going to take 10 milliliters out of that, and then we're going to add that to a new volumetric flask that I'm showing you right here. Then what we're going to do is we're going to add H2O to that new volumetric flask. And we're going to add it to a total volume of 100 milliliters. So if this M1 is our 10x solution, or our 10x super strong solution, we took 10 milliliters out of it, added that to a total volume of 100 milliliters, then this right here, this final other solution here, is a 1x solution. It's a 10th as strong. This right here is 1/10 strength of this. Could everyone give me a Y or an N if they follow that and they understand that? Okay. Great. Now what I want to do is kind of build on that. But I'm going to change the numbers a little bit. I'm going to change some of the numbers. Okay. Now, we're going to change the numbers and we're going to use the formula. Because that 10x to 1x, I think that's kind of intuitive. But let's say that our stock solution had a concentration of 2.4 molar. Don't get caught up and think, oh, well, that's 2 moles per liter. Don't get hung up on that. It's 2.4 molar. I'm going to put that number right here. I'm going to put the units, I'm going to put in parentheses. So that is M1 is our stock solution. So you can kind of think about it as this part, the left-hand side of the equation is I'll call it the old stuff, old solution. We took 10 milliliters of that. So we got this, what's known as a volumetric pipette, and we sucked 10 milliliters out of it. Give me an X if you follow all of that so far, the left-hand side of the equation. Right. Now, the right-hand side of the equation is going to be the info about our new solution. We don't know the info about the new solution until we get all the way over here. Our V2, this is the total volume of our new, and if it's easier for you, you could say our new mixture. You could say new solution or a new mixture. Could anyone tell me in the chat what is the volume of that new solution? And I want you to kind of narrow your focus and be looking right here. We got 10 mils from the old one, and then we added water. We added water to that nice little etched line. So our total volume is 100 milliliters. Now, what I'm going to do is I'm going to grab that part of the that V2 is going to be the volume of our new solution. M2 is the molar concentration of our new solution. Do we know that? Not off the top of our head, but can we calculate it? We absolutely can. How would we calculate that? Well, we calculate it by isolating it, by combining 2.4 times 10. That's going to give us 24. So we're multiplying what's on the left-hand side by one another. And then we're going to divide each side by the number that's available to us on the right-hand side of the equation. These numbers are going to cancel. 2.4 divided by 100 is going to end up being M2 equals 0.24. Our units for that are going to be in molarity. Now, we will go ahead and kick off class on Monday with another dilution calculation. And then percent concentration, which is the last slide in this slide deck. But in the meantime, I hope that this made sense. If it did not, we're going to revisit it on Monday. And I hope that you guys enjoyed your weekend. And I will see you on Monday. Thank you very much for coming to class, everyone. I'm going to stop my recording.